Hello and welcome. Thank you for taking some time out of your schedule to be with me here today and letting me talk about, well, a framework that I really like and I really enjoy using. It's called Invoke, which stands for Dynamic Invoke, and it's an open source framework created by Devolver in C#, and it's designed to help red team operators advance their tradecraft a bit to the next level, a bit more like real threat actors would. One of the many benefits of the Invoke is that it has the capabilities to actually try and defeat EDRs, at least from a userland perspective, so unhooking the Userland hooks. People that are familiar with EDRs know that most EDRs also have kernel callbacks. The thing there is it's kind of hard to defeat kernel callbacks from user mode. It's a bit out of scope of this topic, a bit out of scope of this talk. So I'm just going to zoom in on the userland perspective of EDRs and how you can potentially defeat them using the Invoke. So a little bit about me. I'm Jean-Francois Maes. I'm actually a senior red teamer at Inviso, where I'm also the technical driver of all things red. So I oversee a bit of the technical side of the red team at Inviso. I decide which tools we use and which ones we develop. I am also the creator of redteamer.tips, which is a help website for red teamers, where I occasionally post nice snippets and nice tips, some blog posts as well. Since a few months, I'm also the host of the Voices of InfoSec podcast. This podcast is designed and tailored for people to, well, enjoy listening to in the first place and to help people transition into InfoSec. I'm also the contributor of the SANS Sec 560 and SANS Sec 699, where I'm actually also a candidate instructor for the 699, so that's very nice as well. And I'm also a big devourer of chicken and other proteins. I'm a strong believer of #RedTeamFit, so there you go. So what's on our agenda for today? First, I'm going to talk about, well, I'm going to take you to a trip down memory lane. I'm going to give a small Win32 API primer because you'll have to understand how the Windows API works in order to fully understand what the Invoke can do for you. I'm also going to talk a bit about EDRs and whether or not they are malware. I occasionally like to joke that EDRs are malware themselves. We're going to create our own EDR because I don't want to bypass any high reputable vendors in this talk. I don't want to piss anyone off. So I decided to create my own EDR. Well, it's largely based on a project that Ethical Chaos actually posted on GitHub, but more about that later. We're also going to talk about messing with creation flags in order to thwart EDRs. We'll give a Invoke Primer. Going to talk about manual mapping and syscalls. So that's what's on the menu for today. So let's dive in. So let's talk a bit about pen testing. And when I say pen testing in the context of this talk, I'm talking about, well, infrastructure pen testing and quote unquote red teaming. It depends on your optics of what you call a red team. So back in the early days, this was even before I started pen testing myself, well, things tended to be a lot easier than they are today. Back then, you could just run Metasploit, a Meterpreter session. You didn't have to mess with signatures, or you didn't have to encode anything. You could just drop it to disk even and run it, and you would spawn a Meterpreter shell. Because, well, let's face it, the antiviruses and, well, EDRs, but I don't think EDRs were a thing back then, just weren't as good as they are now, which kind of makes sense, right? It's a good thing that EDRs and antiviruses are evolving over time. But that also means that we, as the offensive point of view, have to evolve with them, because otherwise, well, if we don't have the capabilities to defeat the antivirus or the EDR, then there's not really much left to be done, which would be very nice, but unfortunately that's not the case. EDRs are not foolproof. Antiviruses are not foolproof either. So yeah, there you go. Things started to get a little bit better from a defensive point of view when AMSI became a thing. So that's really nice thing that Microsoft developed. It's open source. It's well, it's not completely open source per se because, well, it's Microsoft. It's definitely closed source, but at least they made it vendor agnostic and they exposed some APIs which are quite well documented in the Microsoft documentation. So any antivirus or EDR solution can actually tap into AMSI, which is quite nice. A lot of the well-known EDRs and antiviruses do so, but contrary to popular belief, not all antiviruses or EDRs do that. So if you have an environment, if you run an environment where your antivirus or your EDR product is not leveraging AMSI, you should question whether or not you have the right product in hand. I'm not going to down talk any vendors or anything, but given the fact that AMSI is completely free, the APIs are well documented, you should ask yourself the question if your solution, defensive solution, is not benefiting from that, why they don't want to do that, because, well, it's a very nice thing to have. Unfortunately, AMSI is definitely not without its downfalls or without its blind spots. I don't know how many of you know about AMSI.fail, which is a project that Flangvik actually released a couple of months ago, maybe even a year ago now. That just is a website that gives you a one-click button for an AMSI bypass. And as you can see here in the slide as well, you can bypass AMSI in about 5 to 6 lines and run your malicious code anyway. But at least it provides you the first layer of defense. It thwarts a lot of the script kiddies, so to speak. At least it's not as easy anymore, like just running a Metasploit meter out of the box without doing any modifications to it or without bypassing AMSI first. So that's already a big win. So that made it a bit harder for us. But what really took the cake is, well, the rise of the EDR. So you have your Sentinel-1, you have your CrowdStrike, your Defender ATP or Defender for Endpoint. You got to have a PhD in Microsoft licensing in order to keep up with all the rebranding. And of course, there are countless others. These are just some examples. So yeah, these things made our lives even harder from an offensive point of view, because now you don't have to just deal with AMSI. Now you have kernel callbacks as well. You have inline hooks as well. And on top of the EDR framework, on top of the EDR software, you have other things as well to take into consideration, such as app blocker, exploit guard, attack surface reduction, and many, many, many more other things. So life for a pen tester or a red teamer becomes harder over the time, which is a very good thing. Unfortunately, even EDRs are still not foolproof. They get better over time as well, because there's a lot of machine learning going on in the backend and a lot of cloud integration nowadays as well. But until that day comes that they are undefeatable, which might still be quite a long time, bypasses still exist, and that's what I'm going to talk about today. So first, before I'm actually going to talk about bypasses, I need to talk to you all about the Windows API, which is dubbed Win32 API. So the Windows operating system exposes APIs in order for applications to interact with the operating system. I guess that makes sense for most of you. The Windows API also forms a bridge from userland to kernel land, with the famous NTDLL.dll as the lowest level reachable from userland. I'm going to talk about NTDLL.dll in a second. So the really important takeaway of this slide is that you'll have to understand that everything that interacts with your operating system in the backend talks or uses or leverages these Win32 APIs. Even for the people that are a bit less experienced in the pen testing field or the red teaming field, you know, like Metasploit or shellcode, doesn't matter which shellcode, well, they still have to leverage these APIs in order to operate successfully, in order to interact with the operating system. So that's a really important takeaway, that you have to understand that the Win32 API is very, very important, both from an offensive and defensive perspective. So let's talk about some of the naughty stuff you can do with the Win32 API. And for this slide, I took the classic DLL injection as an example. So there are about 4 or 5 Win32 API calls that are important here for your most basic vanilla classic DLL injection. There are other ways of injecting DLLs or even shellcode, but just like the most basic point of view actually relies on the following API calls, which is virtual alloc to allocate new memory into a process, virtual protect to change the memory permission so you can actually write something to that memory, write process memory, well, of course, that's to write data to your newly created memory, and create remote thread, which will create a new thread into the address space of the process and actually launch your, well, malicious code, so to say. So as you can see, DLL injection highly leverages the Swin32 API as well. So as a rule of thumb, this is very important to understand as well, you want to stick as close to the kernel as possible. So that means that, for example, the API calls that I just mentioned in the previous slide were all API calls that live in kernel 32.dll. And some of you might know, and to those that don't know, well, now you know because I'm going to explain it to you. Every high tier API call, so every module that gets loaded into a process, actually calls the NTDLL.dll at some point, because NTDLL.dll is, as I already mentioned, the bridge between userland and kernel land. So that means that kernel 32, for example, virtual alloc, the virtual alloc call, will actually call the NT equivalent in the background. And you'll see that in just a minute. A very nice read as well, if you're interested in this kind of stuff, is actually by Rastamaus. The link is referenced in the slides, and the slides will be made publicly available as well. So don't worry about that if you couldn't get the URL from just watching this talk. So let's just take a very simple example loader. As you can see here, this is not the invoke, this is just platform invocation. I will talk about the differences in just a minute. But here you can definitely see that I'm importing kernel 32 DLL in my code, actually specifically calling the create process A, the virtual alloc X, the write process memory, and the create remote thread API calls. So those are the API calls that I actually imported manually into my C# code, and then I'm just leveraging them into the main the main function, the entry point of my application, to actually spawn the new process and to copy my shellcode into the new process and create a thread. So what would that look like? Well, it's actually fairly simple. If I create this, if I launch my demo basic loader and I give it an arbitrary value, for example, notepad, I'm actually going to spawn a new notepad. I'm actually going to hit some keys, hit a key to allocate memory, hit a key to write memory, hit a key to create a thread and launch our shellcode. And when I hit the last key, actually this evil payload message box will show up. And what it's interesting here as well is if you look at Process Hacker, this is a very nice tell that something malicious is going on. Is actually I created in the basic loader, I'm using read, write, execute permissions. So if you would inspect that process tree in Process Hacker and look at the loaded modules into the memory, you'll actually see that there's now a new page created about 4 kilobytes big, which is read, write, execute. And it's the only read, write, execute page in the entire memory of that process. So if I would open that up, you'll actually see that this is indeed a message box payload, because you can see it in the hex dump. As you can see here, evil payload.messagebox. It's actually the message box that I'm going to spawn, as you can see here. So that's a very nice tell, in my opinion, and something to note if you're a defender, to actually look at this kind of stuff. And that's exactly what an EDR will do as well. If an EDR sees read, write, execute into an application, it might actually already send out an alert, because this is not something you see in a typical behavior. This typically doesn't happen that often. And just so you can see that I'm not lying, there's actually a very nice free tool as well called API Monitor, which can actually monitor the API calls that a specific process is making. So here I attached it actually to my demo basic loader to check what the hell is going on in the background. As you can see here, CLR.dll, which is actually the process that is actually loading our .NET assembly, is calling virtual alloc x, which is a kernel 32 call. But as you can see in the call tree, NT-allocate virtual memory is actually being called. And NT, if you see NT, this typically means that that function, that exported function, lives in NTDLL.dll. So that's what I meant with higher process trees and actually trying to stay as close to kernel level as possible. Because as you can see, kernel 32 API calls are reliant on NTDLL.dll anyway. So from an offensive point of view, it makes sense to call NTDLL.dll exported functions directly, because it doesn't really make sense to go higher up. Because from an defensive point of view, EDRs will check the NTDLL.dll. Why? Because, well, it makes life easier for them, because every single higher tiered model will actually call NTDLL.dll anyway. So from a performance point of view, if you just hook all the NTDLL.dll calls, which by the way doesn't happen, each EDR vendor only hooks very specific functions. But imagine, for the sake of argument, that an EDR would hook all NTDLL.dll calls. Well, that means that anything that is higher up in the hierarchy will actually end up calling NTDLL.dll anyway, which provides full visibility into the EDR to check whether or not your API calls are malicious or not. I'm hoping that makes sense. So let's take a look at what the basic loader does. You already saw it in the slide, but I'm going to give a small demo anyway, just so you can see how it works in real life. So this is just my, my basic box. I'm going to launch PowerShell real quick. I'm just going to spawn that basic loader. As you can see, Notepad. So a Notepad actually popped up on my screen. The process ID is 17152. If I would check that in Process Hacker, 17152, you'll see that Notepad is indeed there. It says hit a key to allocate memory, so I'm going to do that. Hit a key to write memory, I'm going to do that as well. Hit a key to launch a thread and a shellcode. Well, if I do that, then there should be a message box popping up, and it does, saying Invoke payloads. So that means that our process injection actually works, our shellcode injection actually works, and the message box pops up. So that's the first demo. If I kill the message box, it'll actually kill my parent process as well, because I used Metasploit, MSF Venom to create the message box payload, and I didn't define an exit function, which means that if I kill the shellcode, I'm going to kill the parent process as well, which is not very OPSEC safe, but well, it's a demo anyway, so it doesn't really matter at this point. All right, so what's so special about NTDLL.dll? Well, NT functions are essentially syscall wrappers, and they will always have the same skeleton assembly, which basically means moving R10 into RCX, and then actually pushing a syscall into EIX. So the syscall here for NT allocate virtual memory is 18H. But this is where it gets interesting, because these syscall numbers are not the same on all operating system versions. So for example, in this case, it's Windows 10. So in Windows 10, NT-allocate virtual memory is 18H, which stands for 18 hexadecimal. But for example, on Windows XP, it could be a completely different hex value. So you can already imagine, from an offensive point of view, it's kind of a pain if you need to hardcode these syscalls into your offensive tradecraft, because it depends whether or not you're on the Windows 10, Windows XP, Windows Server 2008, Windows Server 2012, and so on and so on. So these numbers tend to change based on the operating system version. So you'll have to have a check somehow to see on which operating system you are. So statically using syscalls is kind of a pain, because it depends on your operating system. And luckily for us, and unfortunate for defenders, there's a better way to do this, and that's to actually resolve the system calls dynamically. And that's something that Invoke can do for us. I'm going to talk about that in just a minute. So why do I say that EDRs are malware? Well, it's actually fairly simple. It's because most EDRs, if not all EDRs, actually leverage the same Win32 API calls like malware would do in order to inject their own DLLs into spawn processes. And the reason why they have to do that is because, well, they need to, well, from a userland perspective, they need to hook user functions. So they have to inject their DLL at some point into the process. So you can actually, so they can actually see what's going on from userland. So that's why I'm saying that EDRs are malware. They're just vendor-approved malware, so to speak. So how most EDRs work from userland hooking. This is most is very important there because not all EDRs rely on userland hooks, but most of them do. So in this slide, you can actually see two examples. You'll see an example of a regular function prototype of NTDLL virtual memory. As you can see, it follows the same syntax, the same skeleton assembly code as the NTDLL function like you would expect. So the R10, RCX, AX18H, your syscall and your return value. But if you look at the second function prototype, which is also NTDLL virtual memory, you'll see something completely different here. You'll see that you're actually jumping into a new memory space. And if you would follow that memory space, you'll actually end up into the DLL of an EDR. So you can see that these functions are definitely not doing the same thing, even though they are the same thing. That's because EDRs divert your execution flow into their own DLL to do some arbitrary checks, and then have a decision tree whether or not they will allow you to make that API call or not. If you're allowed, you'll actually return to the normal function, and nothing will happen from a user point of view because, well, it just follows the same flow like you would expect. However, if the EDR deems you to be malicious, your API call will be blocked at that point, and the EDR will send out an alert. I hope that makes sense for everyone. So I already actually gave the answer, but I'm going to ask the question anyway. What happens from an offensive point of view if you create a loader that actually calls NTDLL.dll when your EDR hooks kernel32.dll? I'm going to give you a few seconds to think about that. Unfortunately, this is a pre-recorded stream, so I don't have the chat or the audience with me at time of recording, but I hope it makes sense for most of you if you paid attention to what I'm saying, that if your EDR would hook kernel32.dll and you call NTDLL.dll directly, you would actually bypass the EDR hooks because they're hooking at a level above you and you're actually calling something below that. So you would be, the EDR would be blind to your Win32 API call. Hope that makes sense. I'm going to make it even more obvious. So it really makes a lot of sense. Imagine this very stupid example. So you have a function called hooked function. And imagine from an offensive point of view that you know exactly how it's implemented. So you know exactly the code to follow. In this case, it's just, a print to your out, to your std out, saying I do cool stuff. Well, if you would create another function and you would call it another name, for example, clone of hooked function, and you copy paste the function prototype in there, so exactly the same thing, I do cool stuff. Well, guess what? If you would call the hooked function, you would do cool stuff. But if you would call your new function, in this case, clone of hooked function, you would do exactly the same thing. So that is a bit how using syscalls work. You're going to create a new function prototype using direct syscalls in order to avoid using the hooked function. But the syscall function you created is going to do exactly the same thing. So it's going to work, but it's going to bypass the EDR. I hope that makes sense. So how can we check if this theory does make sense? Well, thank God for Ethical Chaos, because he actually created a very nice blog post called creating an EDR and bypassing it, or something along those lines. And he open sourced the EDR that he created. It's called Silent Strike. It's a bit of a joke to a very popular command and control framework. So Silent Strike is there. It's on GitHub, and well, I basically took his code and I just well, created some new hooks as well in order to detect and prevent the basic vanilla shellcode injection like my basic loader was doing. But I'm hooking on the NTDLL calls in this EDR demo. So my basic loader, which was using kernel 32 calls, is actually going to get spotted by this EDR. And that is exactly what you can see in this slide. So here I have a listener that is listening for my demo loader, basically. It's going to inject the Silent Strike DLL into that loader, and it's going to hook on the functions, the allocate virtual memory, write virtual memory, and create remote thread. As you can see here, if I hit the keys now, you'll actually see a message box showing up saying, oh, yeah, you got detected. And actually at the point where I'm going to create the new thread, I'm actually just going to kill the process entirely, which means that my message box will now not show up anymore. And I can see that here as well in the process hacker. If I would check the loaded modules for my demo, you'll see that silentstrike.dll does get injected, and that places the Userland Hooks. So you'll see that indeed my loader doesn't work anymore because the EDR now blocks it. So let's show that real quick in a demo again. Here I'm going to need two PowerShell prompts, one as an administrator and one as a regular user. The first one is basically just a listener for my demo process, so the EDR Silent Strike can inject into it. So now I'm listening for my demo.exe to spawn, and I'm going to do that right here. Again, the notepad pops up. I'm going to minimize notepad, and you can see injecting process with DLL silentstrike.dll. So if I would now open up process hacker again, and I check 21540, which is demo.exe, I check the loaded modules, I should see Silent Strike in there. And yeah, exactly, it is. So now if I hit that key to allocate memory, you'll see the message box coming saying custom EDR powered by ethical chaos. Allocating read write execute memory ROE detected. So it basically means that the EDR actually hooked my kernel 32 function, checked whether or not I'm trying to well, use read write execute, and well, I do. So it's actually popping up this message box. In this case, it's just a message box, but a real EDR would just send out an alert, of course, without doing this very obvious thing that that an attacker got detected. So if I press OK, I now hit the key to write memory, writing memory, so I get detected once again. And now hitting the key to create a thread and launch or shellcode. If I would hit that now it says, okay, that does it. I'm not going to let you create a new thread. I'm killing your process now. So basically this is a giant cog block preventing me from actually spawning that message box. So if I do okay now, you'll see that the demo.exe actually got killed completely, and just my notepad remains, but no message box actually popped up. So my payload did not get executed. So that is how an EDR basically works in a nutshell. Obviously there are way more things to consider, but this is just a very high level view of how EDRs potentially work. Now, there was, for a very small point in time, something really cool you could do, and that's actually messing with creation flags. So there's a very cool thing that you can do called process creation migration policies. And one of those migration policies was actually to block non-Microsoft binaries from injecting into your process. So basically that means, in layman terms, that from that point on, if your process is created with those process creation flags, you now prevent any DLL that is not Microsoft signed to inject into your new process. So that means that if an EDR vendor did not have the DLL signed by Microsoft, you would effectively prevent them from injecting into your process. Luckily for the vendors, EDR vendors caught onto that. Microsoft caught onto that as well. And Microsoft started handing out intermediate certificates to EDR vendors, so their DLLs are now Microsoft signed. But as you can see here, in this slide, you can see the downloader or the Demoloader, excuse me, with and without creation flagshenanigans. So as you can see here, this is just my demo.exe without any special mitigation policies. If you can see it here, it basically says signature restricted, store only. So that means that from now on, only Microsoft signed DLLs can inject into the process. And how do you do that? Well, from a C# perspective, it's a bit harder to do because you'll have to do some managed to unmanaged memory gymnastics. You have to interop between C++ and C#. So if you're not that familiar with C# or C++, this could be a bit daunting at first, but I guarantee you, if you just look at some examples on GitHub, you actually get a hang of it quite soon, quite fast, and you'll learn how to do this very fast. So if you do this correctly, you actually prevent the silent strike in this case, because, well, it's not an official EDR, so I don't have the Microsoft certificate. You're going to prevent silent strike to inject into the Demoloader, which basically means that you actually evade the EDR because you prevent the EDR from injecting into your process in the first place. So as you can see here, this is the actual create process call. It has extended startup info present because the mitigation flags are actually only able to being set in the extended startup info. So that's why you need that specific process creation flag in there in order to actually use, startup info extended to actually have that mitigation policy present. And if you see it from an EDR point of view, you actually see that the EDR says, well, hey, no problem, man. I'm injecting the process into silent strike, into the demo. But in reality, this is not the case. And even if you would give Process Hacker a bit of time, you'll actually see that Process Hacker itself also can't create a module information anymore because the protection conflicts the requested bytes. So that means because Process Hacker itself is not Microsoft signed, you're actually preventing Process Hacker from injecting into the binary as well, which means that you now lose the nice overview that Process Hacker has as well. So it's kind of funny. I created a small demo called Demo Malware Protect, which basically gives me an arbitrary parent process, in this case Explorer. So it's using parent ID spoofing. That's another common trick that adversaries and red teamers alike tend to use in order to break parent-child detections, which is very powerful. Which is also part of the extended startup information, by the way. It's the same structure that is capable of doing that. So I have the Explorer as a parent process. I'm launching my demo.exe, but my demo.exe now is protected with that mitigation policy, and you'll actually see that silent strike is not injected into the demo.exe, even though it falsely assumes that it is, and I can execute my payload regardless. So that's quite nice. So now I'm going to use my malware protect wrapper around my loader to prevent silent strike from injecting into it. So I'm going to start my listener first. So demo.exe. I'm now going to use malware protect to actually spawn that demo.exe. As you can see here, I'm using Explorer as a parent process, demo.exe, and surrogate will be Notepad. If I launch that, you'll see that indeed my demo.exe spawned Notepad, and I'm going to show you that here as well. So demo.exe, if I look here, you see that the parent is explorer.exe. Obviously, this isn't true because we spawned it from PowerShell, so that's the parent ID spoofing. You see that the signature is restricted to store only. And it means that now, if I look here, it says demo is injected with silent strike. But if we verify that by checking the modules, I don't see silent strike anywhere. No silent strike, even though it says that it did inject into it. So if I now hit my keys, I don't see any pop-ups, but I do get my payload executed once again. As I already mentioned, vendors caught on to this trick quite quickly. You can see here from a tweet from Sector 7 that Falcon loads perfectly with block DLLs enabled and hooks NTDLL. Well, that's because it's signed by Microsoft, so no wonder this doesn't prevent EDR injection. So if you would check, this for example is from McAfee, you'll see that there is indeed an intermediate certificate there from Microsoft. So that EPMPTHE.dll would get injected. But here's the kicker though, that McAfee EDR process also has a DLL called ATP AMSIGuard, and that is not including that intermediate certificate. So that would mean that only parts of the EDR would get injected and other parts that don't have that Microsoft intermediate certificate would not. So that's quite nice to know. However, most popular EDR vendors have all their DLLs that need to get injected signed by this well, intermediate Microsoft policy. So that would completely negate that mitigation flag. So that's back to the drawing board from an offensive point of view. It was fun while it lasted. Unfortunately, it didn't last that long. And here is where it gets interesting, because here is where the invokes start to shine. So .NET provides a mechanism called platform invoke or pinvoke. That's the term that I already mentioned during the talk, that allows .NET applications to access data and APIs in unmanaged libraries or DLLs. So that's the common way of doing things. That's how most developers do that. So they actually use pinvoke in order to include DLLs into their C# code, so they can use those API calls from those DLLs. But by using pinvoke, you actually have some disadvantages as well, because, well, for example, the export address table would actually, the import address table, excuse me, would actually have the reference to your imported addresses. So that makes it easy for well, reverse engineers to just check your import address table, and they would definitely see like create remote thread. That's already quite a red flag, because that's not something a lot of processes need to use in actual behavior, non-malicious behavior. So they would just have to inspect your EIT and they would see that you're doing some fishy things. So that's already a tell. And well, as I already mentioned, AVs and EDRs can actually hook those API calls as well. So you would get detected on the same fashion like the first, like the second demo, where I used my silent strike EDR to actually detect my basic loader. So that makes sense for pinvoke as well. So those are the disadvantages of pinvoke. So why would you use the invoke then? Well, it's actually fairly simple. It's because now API imports get resolved dynamically. So that means that there's no well, there's no mention anymore of any APIs that get imported in your import address table. There's also functionality to evade hooks using manual mapping, using deception even, and syscalls. I'm only going to talk about manual mapping and syscalls in this talk, because otherwise I would overshoot my window. And it has function prototypes already built in for a lot of the API calls that we commonly use in offensive tradecraft. So we can be lazy. We don't have to manually import or manually well, specify those function signatures anymore, because they're already baked into the invoke framework. So that makes it something that we can leverage if we are pretty lazy. And let's be honest, we are all a bit lazy, I think. At least if I can make my life easier by using a library or using a framework, I sure as hell would do so. It's not really that feasible or that, that expected to actually reinvent the wheel. So that's why I tend to use libraries and frameworks as much as I can. So let's talk about, or let's give a Invoke Primer for just a second. So it has a NuGet package, which is a bit of the package manager for .NET basically. But the NuGet package, unfortunately, gets flagged by Defender nowadays. But you can just import the source code, which is downloadable on GitHub anyway, and you can just manually import that into your project, and that is not flagged by Defender yet. It has built-in injection APIs for process injection, so you don't even have to try hard with your injection anymore either. It has just a very simple dinvoke.inject API call to actually do the process injection for you. It is capable of resolving API calls in 3 ways. So you have the standard way of doing things, much like pinvoke would. You have your manual mapping, which is, well, mapping a module manually into the DLL. I'm going to talk about that in just a minute. And you have overload mapping, and the overload mapping is a bit of the deception kind of thing, which is a bit out of scope of this talk. So that's quite nice. So let us talk about manual mapping, because I actually addressed it a few times already during this talk. So what is manual mapping? Well, let's first take a look at how regular processes behave. So every process has a virtual address space. In that virtual address space, there are multiple DLLs present. Imagine you are malware, you want to interact with a specific process. That specific process has kernel32.dll in its virtual address space. Well, you could just call the kernel32 DLL functions of that virtual address space and use that. But the thing there is, the drawback there is that your EDR will also have hooks there. In this case, in this slide, I'm actually using NTDLL as an example. So for example, malware is trying to allocate memory using NT-allocate virtual memory X. Well, guess what? The EDR actually has that function hooked. So that means that you'll get spotted when you try to use that call. So that's not really what you want from an offensive point of view. Luckily, the rover actually thought about that and actually created the manual mapping behavior. So what that basically does is, EDR vendors tend to do their process injection, so their DLL, at runtime. So that basically means when your process spawns, it will inject the DLL into it and place hooks into the address space that is already there. Now, manual mapping actually maps the DLL that you want to use in memory after the process is launched, which means that it is a completely clean copy of a DLL and is not having those EDR hooks in place. So that's pretty cool, because now your EDR is hooking NTDLL.dll, which is present at a specific memory location in the virtual address space. But you actually mapped a copy of NTDLL.dll on another virtual address space location in the same virtual address space, of course, and you can actually leverage that DLL instead, which is completely free of hooks. So that's pretty nice as well. So I actually created, an EDR goes brr, which is basically my demo basic loader on steroids, because now I'm using Invoke instead. I have syscall methods and manual map methods as demo. And for this example, I'm actually showing you the manual map method. As you can see here, I'm using parent process explorer. I'm using Notepad as a surrogate, and I'm actually mentioning that I want to use manual mapping. You can see that I'm actually spawning Notepad with parent process explorer. Process ID is 6608. And if I would check the memory under the address, you'll actually find the manually mapped NTDLL.dll. So if I would compare these memory locations, you can see that they are definitely not the same. The first one starts with 0x2D. This one starts with 0x7F. So they're living on completely separate locations within the same virtual address space. But if you would compare the hex dump of these two memory locations, you'll see that it maps 1 to 1 because it's an exact copy. However, one is actually hooked by the EDR and the other one is not. So if I would use functions from the unhooked or the clean EDR, the clean DLL module, that basically means that I can now leverage my malicious code anyway without triggering alerts from the EDR software. So if you would want to do that manually, it would take you quite a bit of time. Why? Because you would have to, well, first of all, you would have to manually map the process, so the NTDLL in this case, into your virtual address space, but you will also have to take into account all the relocations that you will have to do and relative offsets in order to call the correct exported function, because now it doesn't live anymore in NTDLL, NT-write virtual memory, for example, because you actually manually mapped it into another separate memory address. So you'd have to manually calculate all that stuff. And luckily for us, the Invoke does that magic for us. So that's once again a very, very nice reason why you would want to use the Invoke for manual mapping, for example, because it's just a few API calls and it does it for you automatically, which is very, very nice. It saves you a lot of time. If you can see it here, you'll actually see that EDR goes brr, while Silent Strike is actually injected into the process, but it doesn't really matter because I'm actually using a fresh copy of NTDLL.dll, which is not hooked by Silent Strike, which means that my Evo payload will run regardless. So I hope that makes sense for everyone. So I'm going to give a quick demo once again on how you can do this with the manual map functionality, as I already mentioned. So first of all, I'm going to need, once again, an administrative window to inject my Silent Strike DLL into my Invoke loader this time. So what I'm going to do now is set up the listener. Oh, that's a mistake. It needs to be. All right. And now if I use that EDR goes brr method, parent is Explorer, surrogate is Notepad using manual map. You'll see that indeed the Notepad pops up. You'll see that it's indeed injected. If I would check it out, 15204, the modules, Silent Strike is indeed there. However, if I hit my keys, you'll see that, hey, my evil payload works. You'll also see that process hacker can't really deal with the protection, the mitigation protection that I have on this loader. It's quite nice. So as you saw, the evil payload definitely still triggers even though the EDR is actually looking for it. So that's the manual map method. It's basically the same thing with syscalls, to be honest. So with syscalls, you're just going to use the get syscall stub in order to generate the syscalls dynamically. So it doesn't really matter which operating system version you run. It will automatically give you the correct version. It resolves the correct syscall number for you. And using that, you'll have exactly the same experience. So instead of using a manual map, you'll use syscalls instead, and it will defeat the EDR once again. So if I would demo that, it's going to be exactly the same. So let's use the syscall method. So once again, this got opened. As you can see, it actually injects into that once again. So 2. Silent Strike is definitely there. If I hit my keys, doesn't really matter. Evil payload, it works. There you go. No problem at all. So I hope you can see the power behind the Invoke. I hope you will use it in your C# offensive tooling from now on. And as a closing note, I want to say that the Invoke needs your help. It's an open source project created by the Wover, as I already mentioned several times. I try to to submit pull requests every once in a while as well, because I use the Invoke very, very often. So the goal, the dream, is to have the entire Win32 API eventually ported to the Invoke. But as you can imagine, Win32 API is quite big. So there's definitely still a lot of work to be done in order to fully port over the API. But once that's done, then it's just a dream came true, basically, because then you can just code very, very rapidly, and you don't have to worry about, manually creating those function signatures anymore. So it's really, really cool if we could actually get that to work. So that's why this is a call for help. If you have some time, if you want to code, just porting over some of the C++ functionality into delegates, submitting a pull request, very, very helpful. Thank you very much. If there are any questions, I'll be hanging around to answer them, basically. Thank you very much for your time. Take care. Bye.